Good morning, sorry, good afternoon, good morning, depending on where you are. So my name is Nihal. Today's talk is about real-time interrupt-driven concurrency. Uh, this is actually a framework called RTIC for short. This framework is being used to build real-time systems, and this framework has actually been written in Rust. So pretty much we can build a real-time system without having to leverage something like an RTOS. And that's the idea. So before I get started, Uday, are we recording?
Yeah, started.
All right. Okay. So what will we be covering today? Basically, where did RTIC come from? What's its origin story? The concurrency aspect of it, in the sense, let's talk about concurrency in embedded systems a little bit, just to sort of set the context. And then we also will look at RTIC's features, what makes it really, I'd say fast and also provide features like deadlock-free execution that's guaranteed at compile time. We'll also try and look under the hood. I do have a demo that I've put together, and hopefully I'll have some time to sort of walk you through all the gory details of that demo. Hopefully it works. Fingers crossed. Okay. All right. So, and then we can open it up for questions. All right. So what is RTIC? Well, RTIC is a concurrency framework, as I said, and the idea is you can build it can be used for building real-time systems, but I do see that at some point uh, this framework may sort of be extended to not just be used for real-time systems, but something more. But right now we're talking about real-time systems alone. And in what, if you were to sort of explain this in simple terms, you can think of RTIC as a scheduler. The idea is that RTIC can be used to schedule work on a real-time system using nothing but interrupts, and actually interrupt priorities as well. This idea, when I first heard of it, I was like actually pretty blown away, because it sort of simplifies a lot of things, and as you will see, it's quite an intriguing idea, that you can actually build a scheduler with nothing but a few machine instructions or a few hardware instructions. So the first thing is this particular concept is not particularly required. I mean, this wasn't implemented in Rust first. It was a project out of the Luleå University by Per Lindgren group, and they actually implemented it in C. And later on, it was sort of ported over by Jorge to Rust. And some of the Rust features, like its powerful type system and a couple of other things, have really helped RTIC in here to sort of fully realize its potential, as you will see. The other thing, if you're sort of Googling for RTIC online, you may come across something like real time for the masses. That's the old name. So RTIC is the new name. I don't know if that's good or bad, but RTIC sounds abbreviated, so I think that's better. Yes, embedded real-time systems. Let's spend a little bit of time on when we talk about concurrency in embedded systems, what are we really talking about? So I've just boiled it down to the bare minimum. When we talk about multitasking on a embedded system, I'm talking about systems that do not have a operating system. So pretty much we talk about tasks, and we talk about some shared mutable state. Tasks are some kind of execution context that's independent. For example, you have two different independent execution contexts. We call them tasks, and they may or may not be sharing state between them. The key point in concurrency in embedded systems, as with regular concurrency as well, is safely sharing that state between these execution contexts. that's a prime consideration, because we need data race freedom. We need to be able to work on shared state without sort of corrupting it while we're using it between these multiple execution contexts. And critical sections are, it's one of the tools at our disposal to sort of help with this, where in a critical section, we can actually build a critical section that will allow us to access shared mutable state. And critical sections are just a fancy word, but we can implement critical sections in many ways, depending on what we have available to us. Here in this case, in RTIC specific case, because RTIC's primarily targeted at Cortex-M for now, but there's no reason why it should stop with Cortex-M, because the foundation seem, they seem like they can carry over. So yeah, in RTIC's case at least, we can actually build the critical sections using nothing but the hardware interrupt controller and also perform task scheduling and execution. I'll talk more about this. So yeah, on Cortex-M, we can implement critical sections using one of the following options. We can basically say, okay, disable all interrupts, then access some shared mutable state, do whatever you want, and then re-enable. That's like the bog standard way of implementing critical section. Of course, this does not take into consideration multi-core environments, because you still have multiple cores that can contend for the same shared state. I'm just assuming that let's take into consideration that you have a single core. Let's just start with that. Make sense? Okay. Then the other option you have is, let's say, rather than implementing a critical section by disabling all interrupts and then accessing the shared state and then re-enabling them, why don't we just sort of mask some interrupts and add a few compiler fences? That should also work. Compiler fences to prevent the compiler from reordering your instructions. That's also another option. Then the third option that we have is what we call raise the interrupt priority ceiling. By writing in specifically on Cortex-M, you can write to a register called base pre, and that should allow us to sort of raise the minimum priority level before which you can interrupt the system. All right. So RTIC implements critical sections using the third option. All right. And I have some nice little graphs. I can hopefully they'll be easy to get the mental picture of what I'm talking about. So we look at that. The other thing about RTIC is all tasks that we define in RTIC, other than there are two specific tasks called init and idle, other than the initializing task and the idle task, everything else is just an interrupt. It's just an interrupt in RTIC. All right. Well, actually, in a way, this is quite ingenious, because if I'm only dealing with interrupts, I already have something in, let's say, in a microcontroller, specifically like something like Cortex-M, that already does interrupt handling. It's called the NVIC, right? The nested vector interrupt controller does all that. It does the preemption, does the prioritization. That's all fine. If that's the case, then my scheduler can actually be a hardware-based scheduler. With just a few machine instructions, I can build a scheduler that sort of schedules my tasks, one depending on which one needs to run when. And that scheduler itself is just a couple of instructions. Because keep this in mind, I will show you where the scheduler kicks in, but the fact that we are basing our entire framework on interrupts, and those interrupts are actually handled in hardware, we can build the scheduler also using the hardware. Right? Sort of makes sense, right? Okay. So RTIC's features. I'm going to throw a lot of words at you. This is directly from the RTIC documentation. So these are all the features. Basically, the basic unit of work or concurrency in RTIC is a task. It's event triggered or spawned on demand. The important thing is they're not running forever. They're not divergent tasks. Okay. Message passing between tasks is very easy. in rtic. To talk more about that, message passing is basically when you spawn the task from another task, you can just sort of specify that I want to pass this particular value. Then timers is another thing. It's already provided where we are saying that you want to schedule tasks in the future. This is very useful for something like periodic tasks, right? You want to fire something periodically, you can do this. And then the other thing is the RTIC is a preemptive uh, a preemptive task scheduler, right? Because we're using interrupts, so everything is preemptive, right? And then the data rate freedom that I was talking about is fine-grained, as you will see in the one of the demos in the demos as well. You will see that it's fine-grained, it's priority-based. We are building priority-based critical sections for our code. All right. And then, so I don't have a demo for how you prevent deadlock-free execution because that'll be a little more involved. But you can just take my word that this is something that's guaranteed at compile time, because the way we write the RTIC code, the Rust compiler is actually this is where Rust actually shines right now. This is where it makes a lot of sense to use Rust for something like RTIC, because the compiler can type check all of these things and ensure that we don't end up in a deadlock scenario. A deadlock is nothing but where one task is locked a resource, some resource, and then is waiting on another resource, but that's locked by another task, and the other task is waiting on the one that's locked by the first task. That's like a cyclical thing. That's a deadlock, right? That's not possible over here. All right. And as I said, the hardware does the bulk of the scheduling. So that's a very good thing because you don't have to write a scheduler that is actually software, or rather lines of code. And then all of these tasks are actually sharing a single stack. So this scheduler itself is very efficient in memory with memory. You don't need something like a dynamic memory allocator. And as I said, this is fully supported by Cortex-M devices. Right? Okay, let's look at this under the hood. Rather than talk about it for a while, I thought I actually saw this the same mode of illustration in another presentation by another person in the community who actually is one of the core sort of developers, I guess, on RTIC. So I'm going to use the same method. So let's start with the beginning. Under the hood, when you talk about preemptive multitasking, we simply say, okay, I have this graph over here that says I have 4 tasks. One is idle, and the priority seems to be the priority goes up. That means 1 is greater than 2, 2 is greater than 3. Sorry, 1 is less than 2, 2 is less than 3. Right? Sorry. Then we have time progressing on the x-axis. Okay. So when you spawn a task 1, it starts executing. The green bar is the execution part. The orange dot is the point at which the task starts. It's spawned. Right? The task is doing whatever whatever the business logic is. So when we talk about preemptive multitasking, this is what it looks like. Task 1 spawns, starts executing, gets preempted. Task 2 starts, gets preempted. Task 3 starts. When task 3 is done, then task 2 completes, then task 1 completes. That's sort of the simplest preemptive multitasking example that you would think about. Now, when we talk about preemptive multitasking with priorities, just change that a little. Let's just say that instead, unlike the previous example where you had task 2 immediately start and it was not preempted by a higher priority task. Let's just say that task 1 is preempted by a higher priority task, something like task 3. Then in this case, what happens is you end up with this particular graph where you have task 1, then task 3 runs, then you have task 2, then you have task 4, right? Yeah. Okay, let's look at how this can actually be a problem. So in the previous graph, there's no shared resources. It's just tasks executing happily. They like each other, so they just keep executing. Fine, big deal. So, but here they kind of love each other too much. That's why you see all the red over here. You have task 1 and 2 that seem to share a resource, right? And that's a problem, because what's happening over here is, if you have task 1 that's spawned and executing, and then it gets preempted by task 3, then in that case, task 3, let's say it's a higher priority task, it gets to run, it gets to complete. Then in the second case, task 2 also gets access to the shared resource right after task 3 completes, right? That's a problem. Why is that a problem? Because task 1 was working on it. It was, I wouldn't say rudely interrupted, but it was interrupted nonetheless, right? And then suddenly task 2 says, I'm working on it. So that's basically, that's all bets are off. It's all it's properly corrupted right now, that piece of data, right? That's the problem. That's the problem with shared resources. Now, if we were to do something, what we actually want, in theory, what we were looking for is something like this, where task 1 is spawned and executes, task 3 is preempting task 1, great. And then somewhere, somehow, task 2 is pending, doesn't get to run until task 1 finishes with the resource, right? That's the other important piece. And then only then you say that, okay, go ahead, I'm done. I got the lock first, or I got access to the resource first. I'm going to run first, and then I'm going to hand it over to you, right? So that's good. This is what we want. So how does RTIC actually do this? Well, RTIC doesn't do something that's not been done before here. This is actually part of what's a larger problem called priority inversion, where over here what's actually happening is you have, actually here, what you have is you have a lower priority task which is holding on to a resource. If it's holding on to a resource, you want to ensure that it doesn't have and a high priority task comes in, but it wants the same resource. It wants the same resource. So actually, not this example, but let's just go here. So it wants the same resource, but you sort of end up blocking that high priority task, right? So a low priority task is executing. It has access to some critical resource, and that's the same resource that the high priority task wants. It comes in when it comes in, but it has to wait for you. That's priority inversion, right? Now, that's also another case over here which I've not captured. Maybe I should. That's another case. So RTIC sort of solves this problem, and the way it solves this problem is using what's known as the priority ceiling protocol. All right, the priority ceiling protocol. The way it does this is something like this. All right. What actually happens is in RTIC we temporarily raise, in this case, task 1's priority ceiling. Right? We temporarily raise it to, yeah. And that allows us to effectively say that when you're done, when task 3 is done, because of the fact that I already have, as task 1, I have a priority level of 2, I will get to run. Okay, before I pass over control over that resource to task 2. Yes. Well, this is a super simplified illustration of priority ceiling protocol. There's a little more in there, but the topic of today's discussion is not, priority ceiling protocol, so I'm not going in there. But just to keep this in mind, this mental picture sort of helps, right? Okay. So, in essence, what have we seen over here? We've seen that on a Cortex-M system, we can have something like the NVIC, which is the core peripheral that can do the interrupt handling, that's exactly what it's for, right? So we know that we can preempt, and we can effectively say, okay, which interrupt has more priority versus which one has less, or rather, which task has high priority versus which task is less, right? That much we already can do with Envy. Yeah. Now the only other piece is, how do you actually set this priority ceiling value? Okay, like you need to really set this priority ceiling value to ensure that it does not get, we don't have that problem of data being shared mutable state being corrupted, right? We have that problem. How do we do that? We use the base3 register, and the key point over here is this is being done at compile time. At compile time, you're figuring out all the relevant base3 values. Base3 value is nothing but an 8-bit value. I'll show you. I have a little bit of some Rust code that shows you how we set the base3. But base3 defines the minimum priority to service interrupts. That's what it's trying. It's like saying, beyond this, only then the interrupt fires. Like you get to run. So you're going to use that to figure out which task gets to run and which task doesn't get. So that's scheduling. Okay. Right? And if you notice, all of that is actually being done in hardware. There's very little stuff that you're writing. You're just setting some bits over there and you're done. Right? The only thing you have to do is you have to write this entire. You have to make sure that these base3 values are written correctly, and at compile time these are checked, and they all pass compilation without issues. All right, and there's a way around. That's where rtic being written in Rust actually really helps a lot. Okay, so we'll talk about this base3 thing a little bit more. So here's what it looks like. This is like a small snippet. It's not a full thing that I've put here, just to show you. So there's a function called svcall, which is probably supervisor call. It has a priority of 1. Okay. Now within that, I'm trying to raise the priority of that. I'm trying to raise the priority level over here of this task. So I say raise 2, and raise is on the right hand side. Right? You see the implementation for raise. It's very simple. You're just figuring out the value, which is the 8-bit value that you're trying to figure out, and you're trying to write it to base3. That's it. That's as simple as that. So figuring those values out is the key point, and this is happening at compile time. All right, and then lower is the way you sort of lower. You just write 0. Done. Right? Make sense? Yeah. That's it. So all tasks are just interrupt vectors. They're nothing more. We can safely share state between execution contexts while ensuring data race freedom. We've just seen that. And then hardware does all the scheduling. That makes it extremely fast. Like compare this with an RTOS, and this is on another level actually, if you ask me. Of course, I haven't tested it. I've just tested a couple of tasks, which we will see. So that's in summary. Now what I'm going to do is I'm just going to sort of walk you through. And this is where let's spend a little more time so that we sort of walk through a demo. Okay, I'm not sure how I can show you this. Yeah, can you see this? Yeah. Remove the background. Okay, how do I change this background? None. Okay. Better, right? Okay, so I'm just gonna sort of put it up here. I hope you guys can see it. Huh? Okay. Yeah. So please ignore this piece. This piece. This is not important. That's not part of the board. It's just this is the one that I have in front of me is an NRF microcontroller, and there's two wires. So there's two peripherals on the board, which is one I've turned it into an I2C master mode, and the other one I've turned it into an I2C slave mode. Now this board is capable of DMA. So these two controllers, or rather these two peripherals, are going to sort of talk to each other using DMA and rtic. That's the idea. So it's a pretty involved example. It's not Blinky. I didn't want to use a Blinky because Blinky is just Blinky, right? So let's just do this. All right. Okay. So what I'm going to do right now is I'm just going to show you some of the code and walk you through it. So can you see my screen? Everyone? Okay. So in rtic, the simple thing that we do is firstly, by the way, for folks on the stream and who aren't well versed with Rust, this is pretty much what a Rust project looks like. You start with cargo.toml file, which will allow us to pull in dependencies that we are using to sort of write any of our code. If you want to pull in other words, you're pulling in some libraries that you depend on or your project depends on. So these are my dependencies, and you can see over here, Cortex M rtic is one of my dependencies. The remaining are sort of very specific because I need to do some printing and show you something happening. That is the reason the other dependencies are that. But the primary dependency in this example is line number 11. Right? By the way, I hope everyone can see it, or should I just increase the font size?
I think.
Right? This makes sense? Okay, so that's the cargo.toml file, and then you can sort of hide everything else. The target folder contains all the binaries. I will show you there's just one particular file that's important in there. And then we have a main file. This is where you write your rtic project. Yeah, that's it. That's nothing more. You pull in your dependencies, you write your project, and then you build, release, and push. That's it. Onto the board. Okay?
Yeah.
All right. So I'll just sort of walk through the rough structure or outline of how this is written. As you've probably seen, you always start in Rust when you start off writing your code, specifically for a bare metal environment. You use no standard, as this is what we call a macro. Yeah, macro basically allows you to specify a couple of things upfront. You're saying that this is a no standard project. We are not going to be using the traditional main function, etc., which we would use if we were operating. We're using something like the standard library. We're not using any of that. We're using the no standard library, or rather the core library. Then we pull in some of the imports that we have, the dependencies that we've declared in cargo.toml. We sort of pull them in here on line number 7. Okay, we're using them. Then everything starts within this thing called module app. Okay, the important thing is this module app is decorated with something called a proc macro in Rust. Here you can think of a proc macro as a way to write more complex Rust code in a very simplified way as a user. So the proc macro will expand out. I'll show you the expansion as well, just so that you know. This module contains all of the entire project, or the entire app, basically. That's why it's called app. So we clearly define that this is a device. We're going to use the peripheral access crate, that is the pack of the device. And we're going to use some peripherals, which I just said, the two-wire interface master mode and slave mode. And then dispatchers. Dispatchers are nothing but interrupt handlers. I'll tell you why. And in this case, what we also have is you pull in some imports from here. Again, same thing. You're pulling in a lot of imports, a lot of peripherals. I pull in some GPIO pins. I pull in a GPIO TE peripheral requirement, which I have. I'll talk more about that. Yeah, all of this is just imports. Then because I'm doing DMA transfers over here, you can clearly see that I first instantiate, a static, type over here. I'm calling it DMA buffer. That static type is nothing but 8 bytes, right? It's a mutable reference that is statically that has static lifetime that is 8 bytes, right? It's basically an array of 8 bytes. Somewhere in memory, it's always going to be there. That's the point. Okay, then I have this enum, which is TWIS transfer. Before I come to that, I'll just give you the rough breakdown of what an RTIC app looks like. In RTIC, as I said, you will have a shared, we'll have some shared state, all right? We'll have some shared state, but each task will also have some local state, right? So RTIC, basically think of it this way. You have a bunch of tasks, right? That's the whole point about multitasking. You have to have more than one task, right? You have a bunch of tasks, and then you have some shared mutable state, and then you have some local state, right? Now, with that in mind, what happens in RTIC is the init task that I said, because it's a little different, the init task stands for initialization. It is not an interrupt handler. It always runs when you start your app. It must be there. It initializes your code. It's, for example, you configure your GPIO pins here. You configure your two-wire interface peripherals over here. You configure the interrupt pins. All of those things, all of those, setup that you do, the initialization that you do, is done here. That's predominantly what the init task is for. But the other point that you should notice is that init, on top of init, you have this macro which says, let me just close this for a bit. You see that there's a macro that says init local. Yeah, you see that? That is basically trying to tell us that init has access to a local variable called buff, right? That's init has access to some local variable. All right. So that's another way of saying tasks actually have access to locals. All right. So the point I want to make over here is you can have locals defined in two ways. Locals can be defined in two ways. One is you can put them in this specifically named struct called local that will ensure that items in there are also local. I'll tell you how they're local. Or you put them in this macro and say, this is an explicit definition saying this is local to this task. Or you put it in here. Depends. All right. And then in the initialization function, as you see over here, what I do basically is I initialize everything that I just talked about right now. And then I return these types, which is the shared, local, and init. Okay, let's take a look at the shared. The shared is basically what you just saw over here. This is the only field that's present in my shared mutables, right? So there's something called transfer. I named it transfer, which is basically the DMA transfer types. And then for local, I have two things. If you see over here, I have GPIOT and I have the TWIM, right? Make sense? Those are the two things that I have as local. That's exactly what's being after all the initialization. It's exactly what's being returned from my initialization function. And there's something called init monotonics. I didn't want to implement the timer queue because it's already available. By default, there's an implementation for many different boards. So I just use that. Monotonics is just nothing but the timer. Okay, so this allows us, that way we return some shared mutable state, some local state, and the timer. That's what initialization does for us. Right? Now, in this context, I have three different tasks. I have three tasks. Look at the way I actually have to talk about priorities, talk about locals, talk about shared. It's extremely simple in RTIC. If you take this macro method like just sort of follow the macro method. It's sort of very simple. Look at this. GPIOTE is a task. Okay, because you can clearly see I've marked it as a task. That's how I declare a task. I've declared the task. I said it has priority 2. I said I'll talk about the binds in a bit. I'm saying that it has access to some local state. It has access to some shared state. That's it. And then I go ahead and implement my business logic inside the GPIOTE peripheral. All right. So far, so good. Then there's also this thing called the on-TWIS. On-TWIS is nothing but on triggering the interrupt, which is the 2-wire interface for the slave mode. That's what I mean by on-TWIS. This is the interrupt handler that fires. Okay. So this is the task that fires. In other words, this task also has priority 2. This little binds thing I'll talk about, and it only has a shared. It only has access to some shared mutable state called transfer. So GPIOTE and on GPIOTE and on TWIS have access to the shared mutable state. Right? Yeah. Make sense? Yeah. Okay. Then there's the last piece, which is send TWI commands. So if you've not already figured this out, this is basically the TWIM. This is the 2-wire interface peripheral that's in master mode. So my board has 2 of them. I have configured one for master, I've configured one for slave. Right? And both peripherals support DMA. They are DMA capable. So that's the whole point, to actually do direct memory access. Right? And then I've also declared an idle thing. This is optional, by the way. Idle task is always optional. All right. You can sort of ignore this panic handler. This only comes into the picture when you've written something in your logic that goes terribly wrong. Not the tasks, not the implementation, because that will be stopped right at the compile time itself. When you're executing, you wrote something, you did something that's not right. It's going to panic. This is the handler that's going to fire. So is that a task or is it a loop? This is a panic handler. This is like a idle is a task. Yes, idle is a task. It's a task. It's optional. It's optional. Yeah. One thing that you might have noticed is it sort of looks like Rust code, but we're still inside a macro, right? So there's a lot of stuff that's happening. If you expand these out, there's a lot of stuff that's happening. So we'll expand it out. But so far, so good, right? Everybody makes sense? Yeah. So context is something which is in the task, is it? Yes. See what's going to happen right now. So these 2 tasks on GPIOTE and on TWIS are actually called hardware tasks according to the RTIC documentation, and this one is called a software task. Software tasks are spawned. They are spawned in code. Hardware tasks run because of external hardware interrupts. Right? That's the whole asynchronous part. Right? For example, this send TWI commands is actually spawned by my GPIOTE over here. You see. Make sense? Yes? So you can have both software tasks and you can have hardware tasks. And then the scheduling of those tasks is what you're going to be seeing, how that works, right? Okay. All right. So, I was going to also talk to you about why this binds is there. This binds is nothing but it is binding this task to the interrupt handler. So this task is triggered by, so the interrupt handler receives, let's say, there's a GPIO-TE means GPIO tasks and events, right? Whenever there's an event, this thing sort of fires. The interrupt fires, the interrupt catches all that, and it's going to go ahead and trigger this task. Make sense? Yeah. So this is if you look at this is 3. I hope you can see this 3. Yeah. That's the number. Okay. And then you have GPIOT, which is 6. Right. That's according to the manual for this particular board. Anyway, that's what they're using according to their hardware abstraction layer. But that's kind of the setup. So you have You have an app module. Inside the app module, you declare your shared mutable state, you declare your local state, you declare an init method or a function, you declare an idle one, and then you declare your tasks. And each of those tasks can either have access to some local, some shared, and they are bound to an interrupt. The software tasks are bound to interrupts, but as you can see over here, you see this value over here, right? The software task will be bound to the same value automatically. It will automatically pick it up, right? The software task is also not sort of manually being triggered or something like that. It's also an interrupt, which the code is triggering. So this is a software interrupt that gets triggered, and it gets attached to any empty interrupt that's you declare, any available interrupt that you're not using. You can sort of assign. It'll use that. Making sense? Yeah. Okay. So now all said and done. Moment of truth. Let's actually run the demo. All right. Yeah. Okay. So is this big enough? Yeah, it's good.
Yeah.
So I've sort of put it over here, and you don't need to see much over here. The board, you don't need to see them because there's no blinking stuff. All the print statements, I'll just sort of walk you through what's happening. Okay. Yeah. So let me just go ahead and hit this. So it's idle. Now what I do is, if you see, I'm just going to do one thing. I'm just going to hit there's a button that's called the user button over here. I hit that. I get that. Right? I'm going to walk you through that, but okay. I'm going to hit this again. I don't know if you can see this. I'm going to hit the button again. Yep. Yeah. Make sense? Yeah. So that's the full extent of the demo. Okay. And yes, it took me a while to get the demo ready because it had all these DMA pieces, all these different little pieces that need to get wired up, but it's working now. Okay. So let me just stop this. And I'll just stop this. And then we can move on to the next one. Okay. Oh, wait. Sorry. I had to explain what that was, right? So, sorry. Let me just do that again. Okay. All right. So just keep this in mind. These are your print statements, right? Let's go back here. Let's look at what's happening. When I hit the button, that's basically a button, right? That should trigger a GPIO pin. So that button is connected to a GPIO pin, which I've already connected over here. So if you see here, my board has its button connected to port 100. So that's what I've set up. Okay. And then that's the button I'm using again over here to sort of set it. I hope you see this is all in the initialization step. Now, once that's done, when I hit that button, what's actually happening? The GPIO pin is going to trigger a state change, and this is going to trigger an interrupt, and the interrupt is going to trigger this task. So this task is going to click first reset the buffer, the 8-byte buffer that I have, right? And then it's going to simply just zero out the buffer and print the buffer just for ease. It's going to reset, zero out the buffer, print the buffer, and it's also going to print a new line because this is print new line. Yeah. And then what we do is once that's done, the last piece that it's going to do is it's going to spawn the master mode peripheral. Make sense? Yeah. So right now in the DMA buffer, we've got zeros. We've got 8 zeros. Yeah. That's all we have. Right? So let's go to the software task. So the moment we spawn, that's a software task that spawned, and the interrupt fires, we land here. Right? And when we see this, you see that, okay, I read from address 1A. So that's my slave is actually the address, it's addressed as 1A because I've already, again, in the initialization phase, I've done when I create my TWIS instance, I set my address, right? Okay, So I read from the address, then I'm basically going to go ahead and print it out, whatever I have. Okay. So what did I have? I only had zeros,
Yeah.
right? So let's go see what I have. Yep, looks like that. I got only zeros. Make sense? Not much. So I do a couple of prints over there. Then the next piece is I have to write 8 bytes in there.
Yeah.
Right? So the 8 bytes I'm going to write are 1, 2, 3, 4, 5, 6, 7, 8. That's what I'm going to write. I'm going to do the same thing, print, and sort of exit out. Okay. So when I do my write over here, but here's a key point. When I do my read, I'm doing my read from my master. This is the master peripheral.
Yeah.
I'm doing my read from here. But you see what's happening here? Read command received. And who's reading? The slave. This is the slave. Right? Yeah. The slave has read command.
SPI interrupt, is it?
Yeah. Right to
binds SPI MO.
It's unused. That's the name of the interrupt that we're using. Okay. Like, or rather than interrupt number specifically. The way this HAL is written, it's basically assumed that it's not a SPI interrupt and so on. According to this HAL, that's the interrupt that we're going to be using.
SPI or SPI.
Yeah. All right. So in the slave logic, what are we doing? We're doing nothing much. We're basically going ahead and we're seeing is the event triggered or not. Has there been a state change in the pin for these? If there is, then I have received a command. Also, the address is correct. All of that is correct. I am basically going to go ahead and transfer, which is I'm going to do a read from the DMA buffer and transfer. Right?
Yep.
That's it. Now, once that is done, once that is done, and right now I'm here. I am here. So right after this read address, look at which task triggered. That's the ideal behavior that we wanted. We wanted this task to trigger, which is the TWIS, give us the output, and then we're done. Right? And then the next write, when I do a write, I've filled out the buffer, the DMA buffer. Now I need to go. This will trigger the write command. Write command received. Okay. Right? The write command received, and then you will see here. I'm going to do a read. Sorry, I do a write. Here's a little difference. Yeah. So when you write, the slave reads. When you read, the slave writes. You're asking the slave to read. So it's going to do what? It's going to do transfer. Right?
Yeah.
The master is asking for data. Yeah. The slave is going to send, which is a transmission. The master is asking to write. So the master is going to write. You are going to receive. Yeah. Right?
Okay, man.
So that's why you see over here the TX and the RX are different. It's sort of flipped out. Makes sense? Okay?
Yeah. Okay.
But look at this. The read, the receive, and the prints are flipping so fast. I mean, there's like microseconds over here. I can't even capture that. Right? You see that?
Yeah.
That's sort of the concurrency framework in Rust. In rtic using like leveraging the whole Rust type system and stuff like that. All right, let me take a pause. Let me just pause this because I don't want my computer to crash. Any questions?
So is there any limitation how many tasks?
Nope.
And number of tasks.
Yep. I haven't seen anything where there's a limit because as you can see, right now all of them seem to be all these tasks are sharing a single stack, by the way. So yeah, that's probably the last limitation that you have.
But what are actually saying the memory? Because every task is running simultaneously. Since a particular declared in every task, is there any like partition of the stack, or is it like saying the same memory? If one task is running, it shares the same memory and delete the whole memory, and other task will share the same memory.
No, that's so the way you're thinking about this is this code executes from execute in place, which is in a microcontroller environment, you're doing what? XIP.
Yeah.
Right. So the text or the instructions are actually stored in Flash. You execute from there. Your question is, are we pulling something into memory, running it, and then releasing it? None of that. This is regular microcontroller setup. The only thing we're doing is all of these tasks, the way your code is executing, is using this scheduler. This scheduler is rapidly firing, scheduling your task, then scheduling the next task, scheduling the next task, scheduling the next task. The reason it's scheduling is purely through interrupts.
Are they using any async functions?
Nope.
No. Okay.
The whole thing about this is it's driven on interrupts.
Yeah. So
Interrupts.
between embassy and this.
That's the whole point. This and embassy. So for folks on the call who do not know what embassy is another framework. It's built on top of the async await features of Rust for specifically embedded environments. So embassy and rtic are two top contenders for your possible options.
Yeah.
So in embassy you can do this. You can do pretty similar things. In rtic you can do pretty similar things, but rtic, as you can see, has its strengths. This is preemptive, but embassy is cooperator.
Yeah. You can assign priorities here.
Correct.
Async also, embassy also we can assign the priorities.
Yeah, but that will have
They
to
are
be.
also using interrupts.
You will have to use multiple executors.
No, but they are using interrupts also.
Correct. They will use interrupts.
Yeah.
But if, let's say, a higher priority task comes in and I want it to interrupt the lower priority one, and I'm using my executor will not be able to tell the difference between two priorities. Okay. Makes sense? You will need to use a separate instance of an executor that is of higher priority. That's the difference. Okay. Here this is a little more easy, right? You're just specifying your priorities and you're just going on.
Yeah.
Along. Yeah. Yeah.
You can have a can with this also.
We'll talk to Mrinal and see what happens. So it's not a big deal, I think. I'll tell you why, because your logic is your logic. Right? It's very likely that we can actually do it. Okay. Any other questions? Actually, it's a very good idea. Yeah. Any other questions?
The task that we saw in the example, the priority one, we elevated to priority. Task two is the number one.
Yeah. So that's exactly what's happening, right? So let's say this is of priority 2, right? Which one? On TWIS is of priority 2. So the moment I said read print and I asked you, I said go ahead and read. TWIM.read is what I said, right? TWIM.read changes the state of the slave pins. So it's immediately fired. Yeah? So the low priority task, because this is task, so if you don't specify a priority, the priority is 1. If you if you explicitly specify the priority, it's priority 2. Like you can specify the exact priority. So this is a higher priority. By the way, on the board, the priorities are in the reverse order. Okay. In rtic, the priorities are in the ascending order. Yeah. Yeah. As far as you're concerned, you just use 1 is lower than 2, 2 is lower than 3, 3 is lower than 4. Right?
3 is highest priority.
3 is highest priority if you take 1, 2, 3. Right? All right. But when you set your brace pre values, it's actually ulta.
Yeah.
Okay. Right. Any other questions? And for folks on the call, any questions?
Can we expand the code on?
Yes, I'm going to come to that. But before that, I just wanted to see if there's any questions. Because when I expand the macro, people are going to start pulling their hair right now. Yeah. How many people do you have on the call, apart from us? Okay, a few. Good. All right. So let's look at, now that we've seen all of this, let's take a look at the expansion. Here's the interesting part about the expansion. You don't have to expand it. It is built into the build cycle of rtic. So there's this, whenever you write your rtic project, the expanded Rust implementation, full Rust implementation, will be inside the target folder in a file called rtic-expansion.rs.
Okay.
It is never used. It's just for you, the developer. Okay, so if I wanted to sort of, by the way, it looks shabby like this. If I wanted to clean it up, I've saved my commands just so that I don't have to redo them every time. And there's that. Okay, I run this. All right, that's better, right? So it's now formatted fully. Okay.
Yeah.
So if you see, this is my module. This is like regular Rust code now. This is my module. In my module, I have obviously I have my DMA buffer that you just saw. I have my transfer type I just put there. I have my initialize string routine. I have an idle function, GPI. All of this is the same, at least in the up till this point. Up till this point. Up to this point, all of this is same. Yeah. Right? Then slowly you start to see that this is all this stuff that is being created is the macro expansion. So in the macro expansion, what you have is, I mentioned that each task has its own local shared resources, right? And they also have a timer. So effectively, that is what the macro is expanding to. It's creating an intern. It's creating a couple of internal data structures for local resources, shared resources, timer for each task. Make sense? It's creating one. For example, let's take the first one. This is init. See? Right? This is init. This is internal. So this is the timer. This is the local resources. And then it creates, if you noticed, in the init function, for almost every task, there's this context thing that's passed in. Right? The context is also passed in here. The context is also passed in here. The context is also passed in here. Right? Every task takes a context. Where is that context coming from? Right here. So the macro actually provides or creates a context for each task. The context is nothing but it contains all the things that the task is supposed to be expecting. Like you declared it, you defined that, you said, I have local resources, I have shared resources, then I have a timer in some cases. Yeah, sort of. Rather than you create all of this, macro does this for you. Okay. All right. So in this case, here is a critical section token, which basically means, by the way, one of the things that you need to keep in mind is when the application is running, init cannot be interrupted at all, because init is holding what's called a critical section token. Whoever holds a critical section token can't be interrupted because it's being executed in an interrupt-free environment. Disabled. That's what it means. I'll show you the implementation as well. That's what the critical section token technically means.
Yeah.
Anyway, so and then finally what you have is for the entire initial init function, you see this. Okay. All right. So this is what you get finally. You get your, for example, local resources, you get a context, you get monotask. Now the same thing is the macro does for all the tasks, including idle. Make sense?
Yeah.
So that's sort of what you would normally look at. But here's the other part. After it does all of that, I just wanted to show you something. Here's what happens in the spawn. Like when you spawn a software task, this is the software task I was spawning, right? When I was spawning the software task, you forget about all these other pieces. There's a queue and all that's created. The important piece is it is going to, when it starts, it is going to put this task in pending state, and it's going to return okay. If everything goes well, this is what's going to happen. It's going to put this software in the pending state so that the next time the priority levels drop to its point, it's going to get executed.
Okay.
Right? That's the idea. Now, but the way this is connected, I'll just show you the way this is connected. Yeah, this is the interrupt that we're using. This is the actual interrupt handler. This is the implementation of the interrupt handler by the macro itself for the software. Yes. And look at the last statement. TWIM commands. What is that? That's the software task we define. Make sense?
Yeah.
Right?
Yeah.
And similarly, if you actually look at the other tasks, which is this is a interrupt handler that we defined, right?
Yeah.
This is also calling what? OnTWIS.
Right.
OnTWIS was our slaves logic, which is this. Yes?
Yeah.
And then you also have what is that? Yeah, GPIOT. It calls. Make sense?
Yeah.
That's it. That's primarily what you see in the. So I don't want to go through the complete code because it's a little lengthy and stuff. But these are the basics. These are the important bits of how you how RTIC works as a good concurrency framework and how it's fast and efficient and cool, right?
Yeah.
Okay. Any questions? All right. And before we go, I think I also have I've also put this up on our I've also got
the metrics RTIC and MS.
I have not come across any metrics, but we can look at it. We can go into this. There's different pros and cons for it. The important thing is priorities.
Yeah.
Is how you define them.
This looks much closer to the hardware.
It is. Yeah. So a good question. We haven't seen the performance. Like we haven't seen which one's better. But I don't think it has even come to that point. Right now, it's so fast that we really need a real system to sort of test this out.
We'll know only when more software.
Yeah, when you have like I don't know, some 100 tasks running and then head blowing up, then we'll know.
Someone tweeted Embassy is not so different from RTIC in the feeling, except that interrupts are hidden in async and wait mode.
Yes, that's correct. Who's that?
Here in Twitter it is.
Okay. Okay. Any other questions? Nothing else?
Yeah.
So just check with the folks on the stream. Any questions? Okay, I guess not. So that's it for today's talk. I hope that was insightful. We can go ahead and close the recording, stop the recording, and yeah, that's it today. Thank you.